This is my PhD defense, and my name is Jingwei Liu, and I'm a PhD candidate in computer music department at UC San Diego. So today's presentation will basically cover the following 5 topics. So if you are in my committee, you should already know my research on the Helmholtz machine. So the focus of the presentation today would be to situate this research in the musical context and to enlighten how this research can contribute to music studies. So to get everything started, I want to talk about why we adopt this model, the Helmholtz machine, or more generally, the hierarchical models for the study of music knowledge construction. So in Western tonal music, the classical analytical frameworks, such as the Shanklin analysis and GTTM, the generative theory of tonal music, they all observe this hierarchical architecture, as well as the narrativity, like music as narrative. They also assign different structural importance to the musical phrases and to distinguish them as nuclei and catalyzers, which can be reformulated in a hierarchical way. So, but the question is that what we want to do here is to derive a general framework for musical cognition and studies. It's not restricted. We don't want to be restricted within the tonal Western tonal system. So the question is hierarchical analysis exclusive to tonal music? So to answer that and to look out into the world music, into the more genres of music, it turns out to be difficult to derive a unified theory or framework for the compositional techniques or to analyze the musical structures. So one example I draw here, besides the tonal music, is one theory they developed to describe the electroacoustic music. So this is not a well-acknowledged model, but we can still see here that the basic structure of this analysis is still observes this hierarchical kind of ways from the fundamental level to the deeper levels to be more to be more comprehensive. So a natural thought is that why we use such frameworks, and to answer this, we need to go back to the nature of music. So music is largely dependent on social forms, modes of production, and modes of thinking. So the idea is that music is actually an example of a convergent evolution adapting to an ecological niche. So when the ecological niche changes, so does the musical form. And obviously, not all musics are hierarchical. For example, for music in egalitarian societies, such as the pygmies music, because they think collectively, because of their social form is egalitarian, there is no hierarchy, so their music features a heterogeneous sound idea, which is the polyphony. So if we think from this perspective, then for the music in our modern societies, it seems natural for us to analyze the music and to study the music with a hierarchical model, because in the modern societies, there is naturally something called social hierarchy or social stratification. So the structure of our current motor therapies seems to be hierarchical. And because of this, the musics developed in such a cultural niche are innately or naturally hierarchical in certain ways, like both in perception and in composition. So this is the idea why we tend to use the hierarchical model as our foundation for such studies. And also, because the research showcases that our brain structures, the cortical responses, are hierarchical. So this is not directly related to the musical structures, but because we aim to study a general cognitive functions of our human perception and cognition, it is natural for us to adopt a model that's equipped with such features, for this related research. So next, let me introduce the model of the Helmholtz machine we use here. So the Helmholtz machine is a feedback neural network with hierarchical structures. It features the bottom-up recognition model parameterized by phi, and the top-down generative model parameterized by theta. And each neuron in the Helmholtz machine is a stochastic binary neuron taking values in 0 and 1. And the activity of every neuron is computed from the activities of all neurons from the previous layer. So for at each layer, so the layers, the hierarchical layers in the Helmholtz machine are conditionally independent. And for every layer, the neurons are independent from each other, which means, so this gives the Helmholtz machine the mean field factorial feature. So to describe the recognition model Q and the generative model P, we use a direct production of the probabilities of all neurons in the Helmholtz machine. So the objective of the Helmholtz machine is the variational free energy, where we minimize the Q divergence of the two models, P and Q. Please give me one minute. I need to close the window, and there's some noise. Sorry. Okay, sorry for the wait. Okay, let me continue. Continue with the slides. Okay.
Jingwei, one thing I forgot to ask in the opening: is it okay if people ask questions during your presentation, or you would like to make some breaks for questions?
Sure. I think I have 3 sections, so after each section, people can ask questions. I think that makes sense. Okay.
Okay.
Thanks.
I hope it's okay if somebody feels that they need to ask a question. I would let that be.
Yes. If
Okay.
you need to ask a question, you can unmute yourself or raise hand. I think there's such a function. But because I cannot see everyone's face, so I cannot see if you raise hand here. So you just unmute yourself, and that would be fun. Okay. So any questions so far?
No,
if not, okay, let me continue with this. So to train the Helmholtz machine, the original authors developed the wake sleep algorithm. So where the 2 sets of parameters, phi and theta, are updated alternatively, which means when we update theta, when we update phi, we fix theta and sample a complete neural assignments here to update phi. And when we update theta, phi is fixed, and a complete a neural assignment is sampled from the bottom-up process to update the parameter theta. And finally, after the derivation, we arrive at the local delta rule, which means the update of the weights only depends on the probability of the current neuron and the assignments of the current of the two neurons connected by this weight. So because in the training of the Helmholtz machine, the recognition model Q and the generative model P, they are mutually approximating each other. And also, when we use the weak sleep algorithm, we naturally ignore this self-entropy term, which functions as a regularizer. So the result of the training of the weak sleep algorithm naturally presents a tendency of latent state collapse. So to kind of to respond to this problem, to this latent state collapse phenomena, I designed an algorithm to maximize the interlayer mutual information in every adjacent pairs of the layers, and to diversify to activate more latent neurons, and also to enhance the information passing through the hierarchical layers. So so these are the details. I think I'll skip that. And this is the result when I use this interleaved MIM is mutual information maximization scheme to train the Helmholtz machine. So comparing this result with the previous one, we can see that obviously more latent states are activated, and also the model performance is improved here, indicated by a drop in the KO divergence. Okay, so so as I mentioned, this MIM is actually an auxiliary scheme that assists the weak sleep algorithm to perform better and to solve the latent state collapse problem. And what we actually do here is to interleave this MIM step. Sometimes the ratio we use in this experiment is 9:1, which means we perform 9 weak sleep steps and followed by 1 MIM step. So actually this algorithm, this mutual information maximization, is quite expensive. So actually it takes 20 times the weak sleep sampling, because actually this algorithm is an ergodic search algorithm where we need to traverse all the discrete states in every layer. So although this is an expensive method, but since we are only using this 8 times sparsely, so after interleaving this with the original weak sleep steps, it only takes three times more than the original weak sleep algorithm. And also here I used a control variable experiment where I replaced the MIM step so I replaced the MIM step with the random perturbation. So which means after implementing 9 weak sleep steps, then I will randomly sample the values of the neurons and randomly flip them with a probability of 1/4. So in this way, we can see that we also activated more latent neurons. So the latent states are also diversified because we are using different neurons for the latent assignment. However, the model performance actually degenerates. So this tells us there is no easy way to improve the weak sleep algorithm. So random perturbation is used in some neural networks, like to help the system out of the local optima and to find the global optima. But here, based on this experiment, we can tell that to improve the mutual information, to improve the weak sleep algorithm, there is no easy method. So although this mutual information maximization is computationally and intentionally and intellectually complicated, but it is necessary in this case if we want to improve the model performance. We need to not only diversify the latent distribution, but also find a way to maximize the mutual information here. So, as I show in these pictures, it's only a snapshot of one training step. But because the Helmholtz machine use this online training, where the samples, the inputs are taken in one after the other. So the training actually fluctuates over time. So here is a better sketch of the training result. So we can tell that although the performance fluctuates over time, when we use the mutual information maximization, the KL divergence obviously drops, and it presents a smaller variance. And also, when we use random perturbation, it raises the KL divergence above the original weak sleep algorithm. So here also, I designed a series of control variable experiments to explore the different factors, the influence of different factors on the model performance here, such as changing the interleaving ratios and add some steps at sleep phase, and also other kinds of experiments. So the experiment before, so I presented so far, implemented on this well-formed data set that we synthesized based on some rules. To test this method, I also implemented it on other data sets. So the shift pattern dataset and heartbeat dataset are two synthesized datasets for the toy problems. And we can see here that in well-formed dataset, the mutual information maximization improves the model performance, obviously. And in the shift pattern dataset, which is the original dataset used in the paper, the Helmholtz machine, the MIM scheme slightly improves the model performance, but at least it maintains the same performance, at least as the weak sleep algorithm. The heartbeat dataset is used in the diffusion models, and this is a very small dataset with only 5 data points. So the data point is pretty sparse. But here we can tell that the weak sleep algorithm actually outperforms MIM because in this very sparse data set, the concentration of the latent state actually inversely helps the model to find the correct fate, like to this very small data set. But we can tell that the MIM actually does better at modeling the data distributions because the data are presented with equal probability. So MIM actually presented a more distributed generative distribution here. So besides these toy problems, I also tried to implement this method on the real life data, the famous MNIST digits. So because the Helmholtz machine uses the binary, you use the binary binary neurons. So I downsampled the MNIST data into the binary form, where only 0 and 1, the black and white are presented. There's no grayscales. So this is an instance of the original training data of the binary pixeled MNIST data. So when I train this with the wake sleep algorithm, this is the generation. So we can tell that this training actually converges because generally speaking, the model generates the shape of the original of the data set, but it makes mistakes in the details, and the images are blurry somehow. And after that, I used I scaled this MIM to this large scale data set. And these are 2 instances generated by this MIM scheme. Actually, these 2 instances have no difference. They are sampled from the same model with the same parameters. They're just two different samplings. So I presented the 2 instances here because obviously the second one looks like more approximated, like to the original training data, but actually there's no difference like between the two samples. So I didn't derive any evaluation for the generations here, but based on what we can tell from the eyes, I think we can see that the MIM actually performs better than the wake sleep algorithm. But also it sometimes fails in generating unintelligible shapes and also the blurry images, and it makes mistakes in the details. So, but I think in light of the more advanced neural network models, such as the diffusion model or VAE, I think the generated examples here are not really impressive. It doesn't reach the standard of state of the art. But one thing to notice is that the samples generated here are actually only use the Helmholtz machine of layers, 10 to 20 layers. So compared to the diffusion model, which takes 1,000 layers to train and to converge, here the model obviously are more economic and efficient. So although it doesn't generate really the top the top quality images. So I tried a lot of methods. Some of them works, most of them fail, and I kind of terminated halfway because I was too overwhelmed by this trial and error experiment. But so far this is the result I get. So maybe in the future, if I am more prepared and I have more time and confidence in doing this, I probably will go back to this and see if I can improve this more and see where I can go. But this is what I get so far. So this is for this first section. I think it's time for some questions before I move on to the next section. Any questions?
A quick question here, Jingwei.
Sure.
So to be clear, right? So Helmholtz machine is a unsupervised method.
Yes.
Yes. It's generative, so you generate distributions.
Yes.
Are you using? I mean, there are so many results obtained, and this is not the very best. This is definitely not the best data set for machine learning, but because you can easily get 99 point whatever, right, % accuracy. But you're not using any labels here, correct?
Yeah, there's no labels. The Helmholtz machine is a self-supervised. Yeah, it's self-supervised, and all the data is just inputted as the data. There is no label of what digit it is. Yes.
Thank you. Yeah.
Thank you.
Jingwei, I had a question too.
Sure.
So, so this problem of latent state underutilization, that's a common problem in many neural net models. Not just the Helmholtz machine. So I was wondering if you think maybe these kind of methods can be used for other generative models as well, like a VAE, just to have because a very common thing is that there are nodes in the neural net that are basically not used at all.
Yes. Yeah, I think I have this intention to generalize this method to the continuous states, because so far it's only I only designed the system with the binary neurons. But I think obviously there is a way to generalize this to the continuous state, because the mutual information method is actually not restricted to the discrete or continuous like neuron values. But I think it obviously takes more time and efforts to do that, and it also depends on like whether the neurons are kind of follows the mean field factorial fashion. Here, because the neurons are independent, so I can derive a factorial kind of decomposition here, which simplifies this method. But if the neural networks are more involved or convolved there, I don't know, but this method is actually a quite general method. You can think of as a kind of a theory that as long as you can find a way to maximize the mutual information, then there is a way kind of to implement this method to any kind of neural networks. So yes,
Okay. Yeah, that
I
makes
definitely have
sense.
that intention to do that. So thanks for proposing that. But I don't know when I will have time. Yes, to get back to this problem. Thank you. Any other questions?
Yes, Jim, could I just clarify? So you mentioned that the Helmholtz machine ignores the self-entropy. Is that
Yes.
right? I didn't realize that.
Yes.
So why does it ignore the self-entropy? Because of course that would be the obvious solution to the dispersion problem.
Yes, yes. So because it updates phi and theta alternatively. So when they update theta, they fix phi. So when the phi is fixed, then this entire term is actually a constant. Therefore, when you compute the derivations, actually this term is actually cancelled out when you compute this differentiation.
I see. And so if one looked at the Helmholtz machine as an early version of a variational autoencoder, where you're unfolding the wake and the sleep parts to give you that bottleneck architecture, then the variational autoencoder should be using the same objective function, but without this scheduling problem. Would that be?
You mean the variational autoencoder? Because the variational autoencoder is actually a feed-forward neural network, which means it actually does this encoding and decoding. So it's a different, so it does this encoding to a bottleneck and decoding. So that is an end-to-end method. But here, because actually the Helmholtz machine fold over these two processes, and the latent states, the neural assignments are actually shared in the Helmholtz machine. So that's a major difference of this model to the VAE. And
I see.
yeah, and this hierarchical model actually simulates the brain structure better because it's actually a hierarchical model with bottom-up and top-down processings. But in VAE, it's a simply structure from one end to the other with a bottleneck in the with the bottleneck. So yeah, so although they use the similar objective functions, the neural network structure and the training method are actually different here.
And I guess you could also argue that the Helmholtz machine has this local delta rule, whereas you'd use backpropagation in the variational autoencoder, which again makes the Helmholtz machine more biologically plausible.
Yes, so the Helmholtz machine actually doesn't use a real backpropagation because it simplified the weak sleep algorithm, simplified everything, and eventually you update with this local delta rule. So it simulates these local synaptic connections where only the two neurons that's connected by this weight matters there. So this system is disentangled from everything, like in the upper layers or lower layers, everything is localized. It's not a backpropagation from the beginning to the end.
Yes, indeed. Thank you.
Yes. Okay. Thank you for the question.
Jingwei, I may have misunderstood them. I thought there was a more direct connection between this hierarchical model that you present here, with a particular instance here of the Helmholtz machine and the variational autoencoder. I mean, don't you have this? You claim it is a completely forward architecture, but couldn't you consider in the variational autoencoder that anything below the bottleneck, that's the bottom up progression in this network, in the hierarchical network, and then anything above the bottleneck, this goes back the other direction, going back, right?
Yes,
and that's your
yes,
top down.
exactly.
So
yes,
it explains it a little bit in more detail then.
Yes. Okay. Let me use this. So the VAE actually is something. So this is the input, and then it goes through something, and this is the latent state, and then it goes back to derive the generation.
And I want to say, just take the structure, flip it over. Doesn't that map onto what you have here?
Yes, yes, yes. Exactly. Yeah, exactly. If you flip this over, then it becomes the model here. But the difference is that in the VAE, the two models are actually kind of independent or separated. So they follow two different structures. They sample different neurons, and they don't have to share the layers. But here, if you fold this over, every layer here are shared. So so the bottom up and top down connections actually share the neuron assignment. So these neurons actually shared between these two processes. But in VAE, the two neural networks are independent. So there's no direct relationship between the neuron here and the neuron here.
Okay, thank you. Yeah.
Okay, thank you. Yeah, thanks for the questions.
Just the last one. There are many works on neural net compression, that is getting rid of nodes that are not used. Do you think there is a connection with your work with the MIM?
Sorry, what is the work you mentioned?
There are many works on neural net compression, that is
yes, exactly.
minimizing the size of the model by getting rid of nodes that are maybe not used. So could there be any connection with the MIM as you presented it?
Yes, yes. So definitely, yeah. Yes, I would say. So the work on this neural compression or any compression method actually directly relates to the treatment of the mutual information, because you try to compress or to preserve the most information out of the data set. So definitely if we consider the mutual information here, it is obviously a compression neural network. And the reason why we use this, why we maximize the interlayer mutual information, is to preserve the most information we can throughout the hierarchical layer passings, and to reduce the information loss throughout this treatment. And this is also the key to improve the model performance here, because we try to preserve as much information as we can in the bottom-up process. Therefore, we get a better fit, a better kind of distribution in the listening data, so that we maintain the information from the data set, and we generate the distributions that's closer, that fits better to the original data. Yes. Thanks for the question. Okay. So if there's no more questions, let me maybe proceed to the next section, where we try to apply the Helmholtz machine to implement certain cognitive functions. And here we call it the Helmholtz neural machine. So to situate this discussion in the music context, actually the original Shankar analysis and the generative theory autonomous music, these hierarchical models only feature the bottom-up processing. So it's only a hierarchical feature detector. However, in later studies, the scholars also realized that in musical studies, only the bottom-up processing is not enough to describe the musical systems. And we need the top-down kind of cognition into this research. So one example is this, the distinguish between the compositional grammar and the listening grammar. So this work is developed by the same author of the GTTM. So later on, they realized that only one set of generative grammar is not enough to describe the musical systems. So they need to use the two sets of grammars, one for composer, one for the listeners, because sometimes there is a discrepancy between the compositional grammar and the listening grammar. So the example they used here in this paper is the serial music. So the composers actually composed their piece using the 12-tone techniques, the serialism. However, the listeners don't perceive the music as such. So the listeners perceive the music using their own grammar, maybe hierarchical, maybe something else. So there is a discrepancy between the top-down processing. So we can see that the composer composed by a set of rules here, and the listeners, they construct the structural description of the events of the musical surface based on their own rules. So this kind of difference between this top-down and bottom-up processing is firstly studied in this work. And also, there is a more explicit theory called the implication realization model proposed by Nummer. So here, in Nummer's work, he explicitly stated that there is a bottom-up system and a top-down system in studying the musical cognition and analysis. So he said that the bottom-up system is hardwired, innate, and universal, and top-down system is cognitively learned, stylistically flexible, and explicit. So because the Helmholtz machine features the bottom-up and top-down processing, and so it is natural for us to use this model to perform the functions of predictive processing here. So predictive processing is a Bayesian flip of the bottom-up feature detector. So where it adds the top-down predictions to modulate the bottom-up process. And so the neuronal representations in higher levels generate predictions. So this is a top-down prediction, and it gets compared at lower levels with the sensory inputs. And this process forms a prediction error, and we aim to minimize this prediction error to coordinate our expectations and what we perceive from the world. So there are actually two ways to minimize this prediction error. One way is to change our expectations, and the other way is actually to precise these prediction errors. So the precision is considered as a gain control of the prediction errors, which reflects our belief, our confidence of the expectations or our belief of the world. So attention here is interpreted as the inference of the precisions. And the attention mechanism and the modulation of the bottom-up processing using precisions provides us a way to selectively respond to the sensory inputs. So by putting the different sensory inputs with different weights, we actually selectively patterned our attention, and it makes us available to cope with noisy sensory inputs and filter out the inputs that the brain doesn't predict. So following this line of thought, what we do in the simulation is pretty straightforward. So we simply weight our inputs. So if we train with pure bottom-up feature detector, all the data are presented equal probably to our system. And now if we add this top-down modulation, top-down expectations, then we actually weigh our data inputs by the backwards connections, backwards modulations at every hierarchical layer. And this is, and therefore we can focus on the patterns, what the brain predicts, and ignore the sensory inputs or the noisy sensory inputs. So this is an experiment we did when the system is fed with all the data set with equal probability. If we perform the bottom-up processing without attention, this is the latent distribution we get. And if we put it with the attention mechanism, then only the sensory inputs that the brain expects get through this screening, and at every layer, this top-down modulation influences the distribution of the latent states. So the backward modulator not only adjusts the weights of inputs, restricts the number of potential causes, but it also modifies the distribution of these causes. So this selective attention actually had a wide application in auditory scene analysis. One well-known phenomenon is the cocktail party effect, where we are able to concentrate on the single auditory stream that we intend to listen to, while ignoring all other sounds in a noisy environment. And also, in this musical source separation, we can flexibly switch the attention when we listen to a mixed sound stream, and to pay attention to different sound sources, different instruments here. So another application of the predictive processing is considered that the expectation provides a context for our perception. So, for example, in the visual example, so when we read this middle figure in the context of the in the vertical context here, then we tend to interpret this figure as a B. However, if we read it with the horizontal context, then we tend to interpret this figure as the number 13. So it informs us within different contexts, within different expectations, we perceive things differently. So this has a parallel example used in music studies, which is the common chord modulation. So here, the context is provided by the different case, and the sim chord are assigned different structural importance when it's considered in different case under different contexts. So here we can see that when we use the same example, when we use the same input into the system under different contexts, we actually derive a different latent cause. So this can serve as an example of the flip of explanations. So in previous experiment, we performed the predictive processing at inference time. So for a trained neural network, or for a trained brain model, when we compared the different situations, when we use the backward modulation, and when we only use the bottom-up processing. But what if we train the neural network with predictive processing? So here, so when a trained neural network is when we use a trained neural network on a new data set, then the neural network naturally presents catastrophic forgetting, where it drastically forgets what has been learned, and it will fit entirely to the new data set, and it forget or ignores the previously learned information upon learning the new information. So so the predictive processing can be considered as a way to solve or alleviate this catastrophic forgetting phenomenon. So when we train with predictive processing, actually we provide a contextual guidance from previous attentions, and our previous attention will help the system to assimilate the new information with the discretion based on the previous attentions, based on what we learned previously. And also it filters out certain information the brain doesn't predict, which the brain doesn't think it fits to our previous knowledge. So this type of study is actually more natural to our human nature, because this is this fits better to the learning model or the learning curve of human beings, where we always build on what we learned previously. So this type of learning can be analogical to the development of a music style of a person's lifetime, or the development of music style in a cultural niche throughout the historical line. So where people actually build on what was already there and build on what we previously learned, and add new informations, add new thoughts selectively to form a compact style which connects to the previously learned information and the past. So this is the experiment we did, and also the kind of arguments I want to put here. Okay, any questions? So maybe I can continue with the this. So besides constructing the internal mental representation using and selectively pattern our attentions, on the other hand, we can actually resort to actions to change the environment or change the samples we actually see. So the salience sampling is something that affords to attention, such as the saccadic eye movements. So the eyes are directed towards salient locations in visual space. Therefore, it changed what we see. It changed our data samples, the sensory inputs directly by our external motor actions before it arrives at our brain models. So also another way for the action to take effect is this cultural niche construction, where we act on the environment directly and to change that ecological niche, such as on writing the desired path. And when we change the environment, what we sample, our the salience in the environment changes, and what we sample also changes. So so when we combine the perception and action together, actually we get we derive the action perception loop. So action perception loop is an interactive model that describes the interaction between the human agents, either with the environment or another human agent, or the artificial agent, such as a computer. So this dynamic process described by this action perception loop is actually the basic model for all the interactive systems. So in my qualification writing, I engineered a real-time Helmholtz drum machine model using exactly this structure, where the computer actually uses the Helmholtz machine to generate the music samples, and the user, the human, actually controls or modifies its preference, the dataset, through a real-time interaction, the input using the user interface. So so this is the action perception loop. But actually, here, this data construction thought, because in action perception loop, we not only kind of fit our brain model, we not only learn from the data set, we also use the actions to actually actively change or to sample the data set. So this thought of changing the data set or data construction is kind of singular, actually, if we put it into this machine learning context. So here I did a simple simulation based on this thought. And here we modify the data distribution based on the generations, because the generation actually reflect the agent's expectation and what the agent think the world should be. And here, the data and the generations are actually mutually adapting to each other. And after a few epochs, they kind of reconciled, and it eliminates the outliers. And we can tell that the data distribution or the data formation changed here. So this is quite eccentric, actually, if we put it into this artificial intelligence or machine learning context, where we actually change the data set, and where we actually change the data set, but not only to modify the neural network structures to fit the neural network to the data. So so far, I haven't found a real good way to make this method meaningful in this artificial intelligence world. So this seems to be an eccentric idea, and I haven't found a real way to interpret it, to situate it well in this machine learning problems. However, recently I read a work that is called data distillation, where the methods are essentially different, but they also proposed a way to construct the data set. So what they do is that they distill a large data set to a smaller one that performs equally well on the neural network models. So the method and thoughts, the motivations are different here, but they also proposed a way to construct the data set. So they switched their attention from how to improve the neural network to how to improve the data distribution. So I think there might be some connection or whatever here. So finally, for this part, when we talk about the constructing the cultural niches, it usually requires a group of people in this community with shared expectations, norms, and conventions. So, so in musical studies, this the study of cultural niche is actually essential, especially for ethnomusicology. So quoted from this paper, all musical sound structures are socially structured. So they exist through social construction, and they acquire meaning through social interpretation. So the world music or the general music cognition is fundamentally culturally grounded, and to investigate these cultural conventions of music, we need to look into the constructing of cultural niche, and this is what this discussion affords to the study of ethnomusicology. So this is everything for this part for the Helmholtz neural machine. I think we can have some questions.
So I have a question, briefly trying kind of to connect your theoretical exploration of Helmholtz machine, which I think you kind of clearly presented the idea that you're trying to spread out activation so they're not underutilized neurons, and the results have been some of them positive, some negative, and then you moved to this idea of active inference and somehow the prediction aspect and the active listening. You mentioned affordances in your thesis seem kind of to be in that domain. Now, to my understanding, the first part is about learning, right? It's the back propagation and adding some additional regularization or initial kind of mix-up strategy but it still happens during learning, right? So we do have this kind of a nice wake-sleep metaphor, which is part of the name, right? That, you know, during sleep, you imagine things, and then during the wake, you actually see these things, and you kind of like compare reality to imagination. Maybe that's part of the creative process. And you said that, you know, first of all, there's this other mix-up strategy on each feature level, each hierarchy, which I don't know when it happens. That's part of the question. Is this kind of, if we imagine that this happens somehow during learning, that means that there is some kind of a pause, whether being awake or asleep, where you revisit all your data, right? Because you have this side memory that you have to revisit to create these mix-ups. So one part of the question is, when does that happen? And then the second, and that may be the main question I had, what you refer to active inference seems to be happening, at least what you described, during like listening. It's the inference process. You already have a trained system, right? And this system somehow, you know, unfolds its expectations or what it's trained, and this creates, you know, the implication, realization, and stuff like that. So that seems to me more of the, you know, something that happens during listening, during the, I don't know to call it the wake phase, but inference phase. Can you kind of comment on these aspects? Because it almost seems that they kind of operate in contradictory ways. You show in the first one, you know, how the activation spread out across all layers. In the other one, you show how your expectation actually focus on one neuron instead of spreading, because your anticipations or your predictions, right, or your active inference part forces you to choose only specific stimuli, and so how do you kind of explain this?
Okay.
Contradict.
So okay, so these
yeah.
are basically two different sections. So the two sections don't have any relationship, I would say, first of all. And the mutual information diversification to diversify the latent states is a pure method to improve the model performance. So I want the model to perform better. And also, you see here that in this model, we concentrate on some neurons, which is actually not the case. We don't mean to concentrate on a few neurons and make other neurons idle. The idea is that it changed the distribution of the latent states. So the latent states are not really not really like reduced, but it's but the distribution changed. Although in certain ways, so there's no actually concentration, obvious concentration when we use the predictive processing. I would say only because we filtered out certain parts of the bottom-up processes. It only filters out some data set, but it doesn't change the processing, the neural network structure, or the behavior of the latent neurons. Yes, so these are like two different two different things. And the concentration here, we see that we filter out some sensory inputs, and this what I want to say. So this kind of focus or this attention can be switched, can be changed. So when we change the attention, everything will come back. So yeah, so if we change our attention to focus on this part of the input, then different distribution will come here and different causes will be found. So no information is lost in this process. We only using the different attentions at different times. So the total information. So for example, so now I'm talking here. So later on I will eat. I will do this, do that, do that. My total ability is still there, but at different times, I choose to do different things. I choose to focus on different tasks. So this is what I mean here. Does it answer the question?
Well, I mean, I was wondering if you see any connection between the two, because I mean, could it be that, you know, the second mechanism, the selective attention, will not work as well if you don't have the initial training spread equally, because then you don't have auto switch. You know, if your expectations are very vague, then you don't get surprises in a way, right? So if you learn something and it's always everything is mixed.
Yes, everything is learned mixed here. At least in this experiment, everything is learned mixed. It's only in the inference time. In the inference time, we choose different attentions. Yeah, it doesn't change the training here. The training is only changed in this example. So when we train this neural network on a new dataset, we want to maintain what we learned before and assimilate the new information with the discretion. So this is where the training comes in, and we modify the neural network weights. Yes, but previously in these experiments, we don't really change the weights of the neural network. If you think so, we only change the latent neural assignments, the causes at every layer. Okay. I hope it helps. Any other questions?
Yeah, Jingwei, I just had a quick question.
Sure.
So I guess what I'm not following is, so what is the way in which the Helmholtz machine controls attention?
So it does not really control attention, but because the structure, let me see. Okay, the structure here, the latent causes, so the layers, the neurons actually, each hierarchical layer, they represent the cause, the latent cause. And the different assignments here, for example, we have 3 neurons here. Actually, we have 8 combinations. If we use 0 and 1 here, then we have 8 different causes. So when I choose different cause, it will generate different distributions. And this is how we can consider we have 8 discrete attentions here. And if we perform this disentanglement well, then each different cause should control different aspects of the generations at the surface layer. And when we switch attention at inference time, we don't change weights here. We only change the latent assignment, the latent causes here, so that it's at inference time it generates different things.
Okay.
Yes. Okay. Thank you. Thanks for the question. Any other questions?
Perhaps I could just ask a couple. I like this notion of salience and actively sampling the right kind of data and linking that to distillation. I'm just wondering about the relationship between the first kind of attention as opposed to salience that you've just been taking us through. Is that in some way related to attention heads in transformer architectures? I mean, I appreciate that they're continuous state space models in transformer architectures, but the same, if you like, internal weighting where the context is in the past seems to resonate with your description of how you've implemented attention in the Helmholtz machine.
I think the attention, the concept of attention I use here is actually derived from this paper, this attention identity and free energy. So this is purely an attention mechanism that's used in this brain model in predictive processing. For the attention in the transformer, because actually I don't use a transformer here. So and also this model is not temporal. So there is no past. It only has this fixed length input. So there's no past. So it seems difficult to link this concept with the attention in transformer, because in transformer the attention is used to encode the different weights of the past and to do that. But here, because this model is not a temporal model, so yeah, I haven't really found a way to link this attention to that attention. So yeah.
So the way you implement your attention is by clamping the some higher level latents. Is that how it's done? When you were giving us the example before of the 8 different attentional sets or 8 different combinations of the binary 3 units, how did you actually implement the attentional set or the prior or the context that sets up the attention? Did you tell the model the context had changed?
Yes.
Yes.
So let me see. So the idea is to weight the sensory inputs, because the sensory inputs, the bottom up, is actually fed in with every hierarchical layer. So at every hierarchical layer, I will generate a prediction. If I use certain attention, I have a top-down prediction here generated at every layer. So every layer, the neurons have this top-down assignment. And okay. So I think actually I use a probability here, not the neural assignment, to perform this weighting, because when I sample here at every neuron is stochastic, so it encodes some probability. Maybe this is 0.5, 0.3, 0.8, something like that, and I combine this probability here with this bottom-up probability. So when in this bottom-up processing, it also generates the probability of this neuron being 0 or 1. So these are 2 sets of different probabilities, one derived from the bottom-up process, one from the top-down. And when they meet at this level, and I will use this probability generated in this top-down processing to change or to modulate or restrict. So the distribution here, the probability here for each neuron is actually controlled by both the bottom up and top down modulation. Therefore, the sensory data are weighted differently here, and this is the way I implement it at every hierarchical layer.
I see. I now understand what you mean by the modulatory. Good, thank you.
Okay, thank you. Yeah. Any other questions? Okay, if not, let me proceed to the last part of this presentation of my work. So in this part, I did a totally different work, totally separate work from the previous one. So this is a purely hands-on downstream practical task in pure music generation. So it has nothing to do with the Helmholtz machine, and it's more about how to generate music performances. Here the data set, the data we use is the symbolic data in MIDI-format. It's a piano corpus. And the classical data processing in such a work is proposed in this paper and is used in performance RNN and the music transformer. So here they use 4 different events, note on, note off, for controlling the musical note, and time shift to control the propagation, the time of the note. And here they use 10 milliseconds to 1 second with an equal spaced increment of 10 milliseconds. And also the discrete velocity quantized from the MIDI representation. So this is the traditional data processing. But in this work, we tried to capture the most of the expressivity in the musical performance. Therefore, I used another way of data processing method where I draw on this cognitive Weber's law. So the Weber's law, simply speaking, it depends. It's based on the just noticeable difference, where if the value, if we have a small value, then the interval should be small, and if we have a large value, then the interval should be large. Because based on this just noticeable difference theory, that the increment, the just noticeable difference, is proportional to the value, to the current value. So we actually divide these intervals unequally, and to categorize or to make these different categories of this data processing here. And in our processing, we derived 5 events: the pitch, the time shift, and duration, and the velocity change. So these 3 events are divided by the Weber's law, and we also use pedal. The pedal information actually provides a high-level grouping structure for the nodes, and it may assist in these long-term dependencies when we model the music generation. So this is the data processing method we use here. We try to capture the most expressivity, and the neural network model, because we have 5 independent, not 5 different events to predict here, and these events associated with the musical notes are actually interdependent. So instead of modeling these 5 fields, 5 arguments independently, we use this more precise conditional probability, and at a cost of computational resources, we divided the neural network into 5 separate LSTMs, where we train each model conditioned on the previous fields of the same note. So you can see the input here. We not only input the information, the arguments of the previous note, we also input the current note, the predicted field of the current node into these systems to model this conditional dependency of these 5 events. So after training such a model, the 5 separate neural networks, we actually derive this attention score for these 5 LSTMs. So from this attention score, we can tell that there is a tendency of self-attention, which means for every field we are predicting, the corresponding field in the previous node actually weighs more. For example, when we predict the duration, and then the duration in the first node actually weighs more than other 4 fields. We predict the velocity here. The velocity in the previous node weighs more than other fields. So this is what we consider as self-attention. And also, it has this current state inclination, which means the weights in the second row actually weighs more than the first row. So here we can see that the weights on the first row always weighs more than the corresponding fields in the first row, which indicates that the prediction actually happens with more focus on the current state, the current fields, than the fields in the previous nodes. So all those results here resonate with our intuition of how this prediction should be implemented. Okay. So here are some generated examples. Maybe I can choose to play some. I hope you can hear this. Wait. Okay, let me do this. Okay, so here are some generated examples. I will play them when I can. But the discussion here, or the arguments I want to put out here, is that this data set actually contains the corpus of mostly Western classical music before 1920s. So most of them are tonal music, falling within this tonal system. And the original compositions are more or less situated within this tonal system. However, if we listen to these generations, it actually presents certain contemporary musical features, such as expressive microtiming, drastic contrast in dynamics and register, and polished roughness, expanded sound spectrum, and enriched polyphonic textures. And also it presents this modern musical structure, which we call the moment form, proposed by Stockhausen in his composition Contacting. Okay, let me try to play some of these so that you have a more intuitive impression of what I'm talking about. So this example presents an expanded spectrum. Let me play the first one. Let me choose this one. Okay, here are just some examples of the generated music. So as for why this happens, why this music trained on the classical piano pieces present certain features that's not in the original data, and it tends to behave in a way like the post-tonal music. So we propose two reasons here. First is that because our data processing method, we use the just noticeable difference, it actually reinvents the musical time. So our uneven division of those intervals actually breaks the original metrical structure in the classical compositions. And due to this reinvention of musical time, we direct our attention more on the expressive microtiming and on these small details in the current, in this temporal way, instead of keeping to the metrical structure in the original compositions. And also, the model we use is this LSTM. It's a linear sequential model. And it also breaks the hierarchical structure that's innate in the classical compositions, where we focus more in the moment gestures as the moment form instead of the motion or succession or the plot, the hierarchy. So this kind of informs us to rethink about the computational creativity. So based on Bowden, who proposed that there are actually 3 types of creativity. The first is combinatorial creativity, which is mostly used or referred in our daily lives when we talk about creativity, which means we take some feature from A and some other feature from B and combine them together to create something new. One example is this neural style transfer, where we take the style of one image and the content of another image and to combine them at certain levels and to generate a new image presenting A's style and B's content. And also the blending or morphing in the latent space of variational autoencoders also present this concept of combinatorial creativity, where when we transform from point A to point B along the path in the latent space of VAE, we find some middle point which combines the features of A and B, and and all those reflects the concept of combinatorial creativity. The second type is this exploratory creativity. And I consider all this reinforcement learning or curiosity-driven reinforcement learning falls within this category. So in this reinforcement learning, when we present this exploitation situation, we actually explore the current conceptual space and to find these unspotted things or undiscovered ideas within this current conceptual space, and as we explore this this current space. So the third type is this transformational creativity, and this is what I want to really talk about. And I think this work, at least this simple, I would say simulation, whatever, falls within or represent transformational creativity, where we actually transformed certain dimensions of one conceptual space to another conceptual space. So there is a transformation from the conceptual space because this original data, the original corpus lies within this complete classical tonal system. And when we generate it, when we reinvent it with certain creativity, for example, we use different data processing methods, we use different neural network structures, it transforms these original compositions to a new conceptual space where it presents the features of the contemporary music and also the new musical structures and forms. So this kind of creativity is what I think what this work offers, the biggest values this work affords. Okay, so this is everything for the third part and also for my presentation. So I think it's time for some more questions.
Thank you.
Any questions? Sure.
Well, maybe I would let the committee members ask. I mean, I think the musical examples that you were showing in the last section kind of tied your research to music in more auditory and that's it.
Yeah, and also thanks for Jihad and Shlomo, because I trained this model on this earcom server. Without earcom server, I cannot do this work because it really demands a lot of computation. So thanks for your support, yeah, in this work.
So yeah, I was kind of wondering if you tried also musical examples for the previous chapters. I think you showed some MNIST and some other data sets. Have you considered, the musical?
Yes,
realizing this.
Yes, the research on the Helmholtz machine is more conceptual. It's more conceptually related to musical cognition and perception. So it's not really like the downstream task related to the music examples. Yes, I think I did one when I engineer this Helmholtz neural machine, if you remember, this Helmholtz drum machine, sorry. If you remember that, yeah, this is the work I did in my qualification writing. I didn't include that example here. But yes, I used this Helmholtz machine and tried to generate some drum patterns. I would say it's not a real successful experiment in terms of music, but obviously, I did something, yes, related using Helmholtz machine to apply to real music data and generate musical sounds and phrases.
Okay.
I have a comment on Bowden, on Margaret Bowden.
Sure.
It's interesting that you associate the first type of creativity, the combined natural creativity, to some sort of neural transfer or representation learning, while the second one, exploratory, you associated to reinforcement learning. I think Margaret Bowden couldn't do that at the time because in '98, people were not really, talking about representation learning and reinforcement and deep.
Yeah, but this paper written in 1996 in 1998 is called Creativity and Artificial Intelligence. So actually, yes, they presented some discussions related to artificial intelligence here.
Absolutely. She was the psychologist of AI, but with the AI that she had available at the time. But I think these three categories are still relevant. And talking about the second one, reinforcement learning, it makes me think that in the Helmholtz network, where you have simultaneously the action of predicting things in a forward fashion and the action of analyzing and perceiving things in a backward fashion. It is somehow something that you also find in deep reinforcement learning, where you have simultaneously the system simultaneously learns the world model, that is the rules of the game in a way, and simultaneously learns how to play better and optimize along these rules by trying to make better prediction and trying to generate a good optimal action policies. So I was wondering if there could be a connection between your work on the Helmholtz network and this idea drawn from from deep reinforcement learning, that you simultaneously generate actions and perceptions in a way.
Yes, yes. So exactly, the action perception loop is definitely connected to the reinforcement learning. I think Carl has some work on this, like doing reinforcement learning and the free energy. But yeah, so far I haven't like really generalized this to this reinforcement learning, where I need to do this gradient policy to to find a policy to guide the actions. So the actions here, in my experiment, is pretty simple, pretty simple. It's just to find a way to construct the data set. But obviously, yes, if I want to find a more structured way to guide the action, to construct the data set better, and to construct the data set in a way that corresponds to the agent's intention and also the environment, then definitely I think reinforcement learning and to explore this current state space is essential to give real meaning to this kind of toy problem and or the very naive method that I developed so far. Yes, thank you.
And I would have just a last remark. In Boden's classification, so number 2 is exploratory, and number 3 is transformational. Well, you said that the example that you have built with LSTM was number 3, transformational. I would say that they are 2.5 in a way, because we're still in the world model, set by the data that you've trained the system on. And you still hear music, from the late 19th century, early 20th century, but of course with some ruptures and some with a few transgressions. So it's fine, but I would say it's not yet fully transformatory, because what Boden meant by transformatory is that we have mind maps, world models and mind maps, and we can explore them in a different way, and that's number 2. But then if we break the map, we destroy the map, and we build a brand new map, where in number 3. So, breaking the map is really inventing relativity,
Yes, yes.
We're breaking the Newton map. You're breaking the Newton map, and we're thinking things that were literally unthinkable before we set a new map, which is not exactly the case here. Not yet, I would say.
Yes, yes. So here I'm just drawing an analogy, because if we think about the tonal music to the post-tonal music, there is actually a transformation, a pin here, actually a huge debate there when we transfer from tonal system, when we break the tonal system and we try to move on to the contemporary music. And nowadays, I would say only a very conventional class like schools, they teach the tonal system. They still compose classical music. But obviously, there is definitely a line, a continuously kind of thing between the classical music and the contemporary. So yes, I wouldn't say this is strictly should be classified as a transformational creativity, but I'm just proposing that if we view things differently, because the definition of the transformational creativity is to change, to transform certain aspects of the current conceptual space and to derive a new space. So there is a transformation there. But yes, maybe this work is still not enough to say, it did the transformation. But I would say this is, from my perspective, a way to interpret the value or the significance of this work. Thanks for the comment.
Maybe transformational creativity could be achieved by applying formal operations on the latent spaces, like transforming the latent spaces through topological maybe transformation, and then see what it gives in generation when you generate new material, maybe something
Yes,
like.
yes, definitely, yes, yes. I think that should be a better way to make the transformation in the latent state, but not on the musical surfaces. Yes, yeah, I agree with that. Okay.
Thank you.
Thank you. Any
Okay.
other questions?